Today I'm going to talk about a local version of isodiametric inequality. We've had a separate video about isodiametric inequality. That is the main ingredient in proving that on Euclidean spaces, the top dimensional Hausdorff measure agrees with the Lebesgue measure. Now, if you want to remember the precise statements of, say, whatever inequality, just remember that iso means the same. So what isodiametric inequality says is that among the sets with the same diameter, the ball has the largest measure. So if we are looking at a set E, which is sitting in Rs, so S here is an integer. So the Lebesgue measure of this set will be less than or equal to the Lebesgue measure of a ball, say centered at 0, of the same diameter. So its radius will be diameter of E divided by 2. So this ball, or any other ball that is same translation of this, has same diameter as that of E, but then its measure will be more. So that is called the isodiametric inequality. But because ultimately we know that this is going to be equal, so we know measure of a ball is just this measure of the unit ball times radius to power s. So from this you will get that this is less than diameter of B, which is the same as diameter of E over 2 to power s. But also we know that this is going to be equal to HS measure of E ultimately. Therefore, you have this kind of simple bound on the HS measure of any set. Now the question is, what if we are not looking at sets and using the same dimension in the Hausdorff measure? Then what happens is that you have embeddings in truly larger sets, domains, and this inequality immediately fails. So the isodiametric inequality in this blue boxed sense fails if E is sitting inside our N, where N is strictly larger than S. And why is that the case? It's simple, so we can give simple examples, yet very, very important ones. So here, suppose you are talking at E, which is sitting in R2, and you're looking at one-dimensional Hausdorff measure. So here S is not going to be necessarily an integer, but for pictures, I'm going to simply deal with the integer dimension. So this E is sitting inside R2. It's a line segment and it has some H1 measure. And we want to compare when is it comparable to diameter of E. So W2 is equal to 2, which kills that 2 in the denominator. So H1 measure is really just diameter. You can see that they agree for line segments. But now you can just add a parallel line to this, pretty close to it, and you can also avoid a buffer zone at the end, so that this new set, which is E prime, is 2 copies, will have the same diameter as E itself, because just compare the farthest pair of points from one another. But H1 of E is almost twice H1. H1 of E prime is almost twice as that of E. And you can do this again and again, so you can add other parallel lines, and you can even have countably many of them. So you can drive H1 to be very large while keeping it constant. And that means an inequality of this sort cannot hold. Example 2, which I unfortunately have to fit into this part, is when you have E again sitting in R2, and you can just have another line intersecting it. Again, by doing this, you never increase the diameter, but every time you add another copy, you add to H1 measure. The theorem that we want to talk about today then is kind of surprising given these examples. It says that if you have a subset with finite HS measure, then locally around almost every x in E, in your set A, we do have an almost isodiametric inequality. So the inequality you see here is what we had in the blue boxes, and this is not 1 but 1 plus epsilon. However, epsilon can be chosen arbitrarily small. So let's read this more carefully. The only assumption is basically that A has finite HS measure. Then at almost HS, almost every point in X, we have the property that given epsilon positive, that means if we want to get an isodiametric inequality up to this error term, then you can do so at the scale of delta. So for this epsilon, there is a delta such that if you have a ball, which we assume is closed, but I don't think that's any essential requirement anyway. So if that point, remember at this point, X is fixed from here. So if the ball contains the point X, and diameter of that is at the scale delta, is smaller than delta, then the isodiametric inequality holds. That means the part of this set A inside B, you can also say that this is just the intrinsic ball in the space A, because that's in relative topology, that's exactly the ball in A. The measure is less than this quantity. Of course, if S is not integer, you cannot really say this equals the Lebesgue measure of the ball or anything, but the analogy is there. So I'm not going to prove this, but let me draw some more pictures of showing what is going on here. Okay, let's test this theorem, which is what you should always do when trying to understand the theorem. So try to understand the theorems before you try to read their proofs and understand their proofs. And one way to understand theorems is trying to break them or push their limits. So we saw the problem with not having isodiametric came from having parallel segments closer and closer to this set, and also having intersections. Now, for example, if you take your point, now I want to need this to stay alive, I'm going to need a lot of colors. If you take this X to be here, because from here to here, a whole line segment is there, you cannot ignore all of them. So it's not like a negligible part of it. So definitely you have to do something for such X's. And we see that first of all, you cannot have infinitely copies of line segment. That is ruled out by this requirement that this is finite. So you cannot have parallel copies that each has a minimum amount of length. So that means only finitely many are allowed in this picture. That is for example, one reason why this requirement is there, and also a counter example that this assumption cannot be dropped. Anyway, so why is the claim true for such an x? Because at this very red point, there does exist some delta positive, so that if B contains the point x and the diameter of B is less than delta, then B intersection with A picks up only one segment. It doesn't see any of the neighbors because there are finitely many. There is this closest line segment, of course, even that means this tiniest gap here, you take it to be your delta. The claim is that for every epsilon you can find the delta, and now I'm giving you exactly that delta. So you take the worst, the closest parallel line to it, there is still a positive gap, only finitely many. If you take this delta less than that, and you take a ball with diameter less than that, because the ball is pinned to the point x, it is required to contain the point x, you are reduced to only that line segment which contains it. And of course there you're looking at a segment in line which definitely then has this property. So that's how the theorem works. For this kind of, say, apparently bad points, you get rid of multiple copies by this requirement. How about the points where this branching happens? If you take this x, okay, before that maybe, let's look at, let me switch to blue. So if you take x's anywhere else, which looks quite nice, then you take delta tiny enough so that you're, again, looking at basically just the line segment. To have this property, you really need to basically, up to measure here, you can always have tiny tentacles, I will show in a minute. Up to measure, you have to be looking at line segments. So for such x, we see that there is always a choice of delta, which puts x completely away from any branching, any copies and things like that. So the next type of bad points are the branching ones. So what happens at such an x? At such an x, you can never get rid of this property that this actually will not hold. It will be the other direction. Because no matter how small you take that delta, if you take a ball centered around this x, there's always two copies. So this is always twice. The h1 is twice this much, and it will, so the inequality will fail if you take epsilon smaller than 1. So these points are actually among those points which you have to sacrifice. That is why the theorem says it holds for hs almost every point in x. Indirectly, if we believe in the theorem, this is saying that the type of points where the amount of points where this branching happens, these dots, all of such branching points will constitute only a set of hs measure 0. Okay, so that's another way this result begins to hold. Next, I'm going to talk about a bit more subtle example. And that is to show you that the pictures above are not the most complicated you can imagine. It's not the case that, okay, this example is supposed to show you that it is not the case that most points have these delta neighborhoods where where the set looks like a line segment. So here again, we're talking about S and n equals 2. So definitely my picture above had that property that most points had some neighborhood where things become a genuine interval. But this doesn't have to be the case, and still you will have this isodiametric inequality. The way to construct this example is to take a dense subset, for example, the rational values. Of course, I can't draw all of them, and add branches at those points. But they have to have varying heights, and most of them have to be very small, because at the end of the day you want h1 of the set to be finite. So for example, if you enumerate the rationals q1, q2, and so on, you can have a line segment of length 2 to negative 1 assigned to that one, 2 to negative 2 there, and so on, which again, if you sum them up, still you have finite length. Therefore, for example, if you pick any point along this, no matter how small a delta you take, you will never see a line segment, because there will always be tentacles. The theorem says that for almost every point in the line, because you cannot ignore all the points here, you cannot say all these points are among the exceptional points, because h1 of this line is not 0, it's positive. So the claim of the theorem must actually hold for almost every x here. And then again, on the other hand, we have that no matter how small a delta you take, there are branchings near there. So how come you still have this property that, okay, if you take a ball around this point with small enough diameter, then h1 of your space intersection with B will be smaller than 1 plus epsilon times the diameter of B, which is just this length. How come that the set around this line segment, although it has a lot of branchings, infinitely many points, every rational here has one, still satisfies this? That's where this epsilon comes from. Just that epsilon room lets you have these branches. So these branches are infinitely many, but their total length does not contribute even epsilon percentage compared to that. So this whole thing is about relative sizes. So relative to this diameter, the additional length that comes from vertical branches only amounts to less than epsilon percent contribution. The truly bad points will be those where the branching is actually significant. So if you take epsilon quite small and you take this x, then here this will be among the exceptional points, because, well, the contribution from this is not negligible even compared to this. So this will be a bad point, but how many long branches do you have really? Not that many. So if you give me any epsilon, only a finite number of these branches have contributions, say at the scale of epsilon. The rest will become really negligible tiny ones. If you're not completely satisfied, you want to have more fun, you can also have new class of tentacles along this vertical line. For example, you can have again rational numbers here, and then these whose sum of length, for example, contributes another 2 to negative I. So that ultimately, again, h1 of the full thing will be finite, because, well, you had one, you had summation of these, you have another summation of these. So that if you do this, then no point is a clean point. No point no neighborhood of any point is a clean, honest line segment. But it's still, the measure of this is finite, and then the claim of the theorem holds that almost every point has some neighborhood where this quantitative isodiametric inequality holds. And last but not least, I want to emphasize this assumption that X belong to B. Why would you want B to necessarily contain X? For example, in this picture, so you have this X, the ball is not centered at X, but we require that it contain it. So let me draw this, try to duplicate this rational points stuff here, and maybe rational points on these two, and I want to add just a few more branches for fun. Okay, so you take your point, say X here. You can have a ball starting here, ending here, so this is the center of the ball. That's allowed. The inequality holds for that. Or you could have a ball going this way and until this point. The only requirement, of course, is diameter is less than delta. Or you could have a ball really centered around X. So balls are not necessarily contained around X, but they have to contain the point X. Somehow it seems an artificial condition, because you can have a ball around here, from here to here. This has delta diameter. It doesn't necessarily contain X, but isn't it in a neighborhood of X anyway? Maybe twice the ball actually contains X. So it's in that neighborhood. Then does this inequality hold? Still, if you allow X not to be inside B. The answer is no, and the way to do that is as follows. So I have to zoom out my picture a little bit. Okay, you have your point X. You want to prove that something is true for a delta neighborhood of X. Okay, and for all balls smaller than delta radius. Okay, suppose I have this shape here. Okay, this shape, and then it's attached to here. So if I take, this is delta. If I take this ball here, okay, this ball definitely has diameter less than delta, and it's not too far away from X either. So distance of B to X is also less than delta. So this ball definitely is in the delta neighborhood, and itself has diameter less than delta. But obviously it is not true that H1 of A intersection with B is less than 1 plus epsilon. So epsilon here is, say, 0.5, because that is twice. So it is twice the diameter of B. So we see that it failed. And this is not a counter example to our theorem, because this apparently insignificant condition wasn't provided here. So this is where this becomes significant. This is saying that you can take balls, if you want to take them smaller in diameter, your diameter has to be less than delta, but doesn't have to be as big as delta. It can voluntarily become way smaller than delta. So you require this, but maybe diameter of B is actually 100 times smaller than delta. this requirement here is saying that if you want to take a smaller ball, you have to get closer to x, because a smaller ball and a smaller radius brings you closer to x. So you cannot cheat and take a ball that is in fact farther away from the point x. So this is pinning down the balls to neighborhoods of x. If you take smaller balls, you have to move closer to x. So that, again, this inequality is up to some scale. When you look globally, for example, why this inequality holds for this green ball is because this part, when you compare to this part, is winning. So the additional, this plus part here, is negligible when you compare to this global one. Maybe my picture had to be a bit smaller for this part to make it more convincing. But so when you look at the larger ball, these extra tentacles become negligible. But then if you move in and choose this ball, which is smaller, then that becomes an issue. And this property is saying that, okay, if you want to zoom in, you cannot zoom in anywhere in the delta neighborhood. You have to come closer to x. So hopefully that was clear. You can draw your own examples, of course, and think a little bit to see why. So with these examples in mind, let's go back to our main theorem and read the statement again and maybe appreciate its depth a little bit. In my next video, I want to talk about a version of this that is going to get rid of balls, so that these become just sets, and we get closer to this one. Here, E is not necessarily intersection with a ball or something. That is contained in our paper with Piotr Hajwasz called the co-area inequality. This theorem I took from Mattila's book. Maybe a final remark will be that its proof is based on a density type argument. So we've been talking about density of sets. You define a version, a variant of that density, which is literally putting this in the denominator of this, and then taking the worst case. So taking a supremum of all such fractions, and then we need to prove that that supremum goes to 1 when delta goes to 0. So that supremum here you define, and then you take limit delta go to 0, you define it as a density. So this is called spherical density rather than the previous density that we had, the difference being that there the balls were centered at the point x. From that, but the proof ideas are similar, using covering and definitions of Hausdorff measures and spherical Hausdorff measure, which is a variant of Hausdorff measures, and from there you prove such a statement. Okay, so a very nice result has been used in my own work on co-area inequality. Again, I will talk about that. Local isodiametric in the general setting of metric spaces in my next video, but still this is very interesting already in the Euclidean case. Until that video, have a nice one. The work is being busy, and I'm busy doing a couple things research-wise, so that's why I'm not able to update as fast as I wished. But you please keep up watching old videos, and as we have covered a lot, and please also subscribe to the channel so that we can keep going. Thank you so much.